Assalamualaikum warahmatullahi wabarakatuh. So today my group and I are going to be presenting about the PHY or particle-induced X-ray emission, which is a highly sensitive, non-destructive analytical technique used for a simultaneous multi-trace elemental analysis. It is capable for detecting a concentration down for part per million ppm or part per billion ppb. Fix their origin. The core principle of this involves bombarding the element with a heavy charged particle to produce a characteristic X-ray. This was discovered in 1910s and 1950. However, in 1970s, Professor Sven Johansson from Lund University, Sweden, alongside his colleagues Roland and Thomas, has discovered a newer modern method to develop the pixel. He is now known as the modern father of pixel. So the reason behind this method is mainly to replace the destructive testing method such as the atomic absorption spectroscopy, which requires sample dissolution or the grinding of the relic artifact itself. Secondly, previously used electron-based method generate Burma-Stralong noise. This is obscuring weak X-ray signal and hindering trace element detection. Thirdly, with the help of Professor Swain himself, he developed cilium lithium detector. Using cilium drifted silicon with the proton, this could significantly reduce breaking radiation, resulting in a much clearer signal. So, industrial application of it. First, there's the artwork and cultural heritage conservation. Because of the pixel, which is non-destructive elemental analysis, this could use for authentication preservation, such as for identifying pigment, map corroded layer, authenticate artifact, and develop conservation strategy. Second, for geological exploration and mining, this could help in quantifying the mineral composition, detect the rare earth mineral elements, optimizing the ore processing, and later to trace metal contamination of the area. Third, the environmental particulate matter and air quality testing. Because of the method, they could use the pixel to trace the element identification in airborne aerosols such as the characterized PM2.5 and PM10, determine the pollutant source, monitor metal deposition, and assess air quality impact. Lastly, the biomedical cell and tissue analysis. This could help in mapping the microdistribution of essential or toxic element in the body. So it's either in the subcellular mapping and then trace the metal and bioaccumulation inside the cell and later to study the metal proteins and state the disease state diagnosis. So that is all from me. I let my friend take from here.
Pixel has important applications in space science. Scientists use it to analyze meteorites and lunar rocks to determine their elemental composition. This information helps researchers understand the origin and evolution of planets and other celestial bodies. Pixel is also applied in food safety to detect toxic heavy metals such as lead, mercury, and cadmium in food products. It can also measure the essential minerals like iron, zinc, and calcium. This analysis help ensure that food products meet safety standards and are safe for human consumption. Many industries use pixel for quality control. It helps verify the elemental composition of metals and alloys, detect contaminants, and ensure that products meet manufacturing specification. This contributes to improve product quality and reliability. Next is related theory, which is Moseley's law. Moseley's law was proposed by Henry Moseley in 1913. Moseley's law states that the frequency, or equivalently the energy, of characteristic X-rays is directly related to an element's atomic number. Since each element has a unique atomic number, it also emits characteristic X-rays with unique energies. In PHY, the detector measures these X-ray energies and compares them with known reference values to identify the element present in the sample. Therefore, Moseley's law provides the theoretical basis that makes elemental identification in PHY possible.
The fundamental principle of particle-induced X-ray emission starts when a high-energy proton beam is directed onto the target sample. So when this proton collides with the atom, it transfers enough energy to eject an inner shell electron, usually from the K shell. So this will create a vacancy and makes the atom unstable. So to become stable again, the atom release the energy in the form of characteristic S-ray. So these S-ray are unique for every element, which make them useful for identifying the element that present in a sample. Right. So to understand why these X-ray are unique, we first need to take a look at the electron energy levels in an atom. So as shown in the diagram, electrons are arranged in different shell, which are there is K shell, L shell, and M shell. So the K shell is the closest to the nucleus and has the lowest energy level. So when an electron from a higher energy shell moves down to fill the vacancy in the K shell, so the difference in energy is released as a characteristic X-ray. So since every element has a different electron arrangement and also energy level, so the X-ray produced also have different energies. So this is why each element has its own characteristic X-ray and allowing particle-induced X-ray emission to identify different element accurately.
This diagram illustrates the principle of work of particle-induced X-ray emission. First, a high-energy proton beam, typically between 1 and 3 MeV, is directed onto the sample. When the proton interacts with an atom, it transfers sufficient energy to eject an inner shell electron, usually from the K shell, and creating a vacancy. Since the atom becomes unstable, an electron from a higher energy shell, such as the L or M shell, moves down to fill the vacancy. During the electron transition, the energy difference between the two shells is released as a characteristic X-ray photon. Because each element has a unique electron structure, the emitted X-ray has a unique energy that acts as an atomic fingerprint. Finally, these X-rays are detected by X-ray detector, and the resulting spectrum is analyzed to identify the element present and determine their concentration. This diagram explains how the PISE spectrum is used to identify and quantify the elements present in a sample. First, in step 1, we examine the position of each peak in the spectrum. The x-axis represents the X-ray energy in kiloelectronvolt, while the y-axis represents the number of detected X-rays. Each element emits characteristic X-ray at unique energy, so every peak acts as an elemental fingerprint. Therefore, the peak energy identifies which element is present. Next, in step 2, we analyze the peak intensity, or more accurately, the peak area. A larger peak means that more X-rays were detected from the element, indicating a higher concentration of the element in the sample. Finally, in step 3, the analysis software combines both pieces of information to generate a PISA analysis report by listing the detected elements together with their concentration. PISA have many benefits of its application, such as it can detect trace heavy metal in air, water, and soil. It also supports pollution monitoring and environmental protection. Other than that, it helps for non-destructive analysis of artifacts. It can preserve valuable historical objects, and it also can measure trace elements in biological tissues. Other than that, it can assist in disease and nutritional studies, and it help characterize thin film in semiconductor. And the last one is it support quality control and material development. In conclusion, PISA combines high sensitivity, rapid analysis, and non-destructive testing, that making it an effective technique for elemental analysis across a wide range of scientific and industrial applications.